Hey grade 12s, and welcome to question 5 of this paper. So in this paper we're going to be working on the trigonometry section. So that is question 5, 6 and 7. So we're also going to work on the 2 and 3D trigonometry as well. Okay, so question 5, 5.1 says, if sine of 40 degrees is equal to p, write each of the following in terms of p. And then the first one that we have is sine of 220 degrees. Okay, so I hope you guys see the pattern that has been going on. You will notice that with your trig diagrams, they'll usually give you these ones. So you should make sure that you are prepared for these ones. Okay, so you see that it says sine of 40 degrees. If you think about 40 degrees on a Cartesian plane, that is an acute angle. And if we had to measure that angle, we'd really measure it like this. So 40 degrees will be measured from here, and then it's just 40 degrees. So it means that your line or your radius is like that, and then that's the angle that we have there. That's the 40 degrees. And they tell us sine of 40 degrees is equal to p. Well, when you think about the function of sine is speaking about the opposite side over the hypotenuse. So since sine of 40 degrees is equal to p, right, it means that p is your opposite side. And so what's your hypotenuse? Well, the denominator of p would be 1 if you wanted to put a denominator of p. So it means that here in this, when we go ahead and draw a line perpendicular to our x-axis, where we have 40 degrees, the opposite side would be p, so there's p, and then the hypotenuse would be 1, and there's 1. So you see that the only thing we need to find is the adjacent side, or the value of x. Okay, so you can use Pythagoras to find that by saying x squared is equal to, so the hypotenuse squared, which is 1 squared, minus the opposite side squared, which is p squared. And then, of course, if you simplify this, 1 squared is just 1, so that's 1 minus p squared. Then if you want to solve for x, you square root both sides. Now, yes, it is going to be plus or minus, normally because when you square root both sides in an equation, you have a positive and a negative solution. But the thing is, as you can see, the x value, right, this number over here is positive. So we don't have to take the negative, you can just take the positive. Therefore, x is equal to the square root of 1 minus p squared. So that's what x is. That is root 1 minus p squared. Okay, now that that is complete, we can actually solve for what they asked for. Okay, so sine 220 degrees. Remember, the reference angle they gave you was 40 degrees. So you know that everything just needs to relate to 40 degrees. That's all, okay? Now we have an angle that is quite big. You can go ahead and reduce this angle. So use your reduction formula. If you think of 220 degrees, which quadrant would that lie in? That would lie in tan quadrant, the third quadrant, where we're going to have 180 degrees plus theta. So if you were reducing that, that would be sine of 180 degrees plus what gives you 220 degrees. That would be 180 degrees plus 40 degrees. And there's our 40, okay? Then if you reduce this, of course, you're going to get negative sine 40 degrees because sine is negative in tan quadrant. Then what is negative sine 40 degrees? Well, if sine 40 is p, negative sine 40 would be negative p. And that's our answer there. Okay, moving on to the next question. In the next question, we have to find the size of cos squared of 50 degrees. Remember how I said everything needs to relate to 40 degrees? If you think about it, if you take 50 degrees, right, you only have to add 40 degrees extra to get 90 degrees. And you know that when we are speaking about angles that add up to 90 degrees, okay, we're going to have cofunctions. So it means that we can actually change this, okay, to the cofunction of cos of 50 degrees. So we have cos squared 50 degrees. And to make this more understandable, I'm going to rewrite it like this: cos of 50 degrees all squared. Okay, it's not usually like that, but I just want you to see what's going on there. So we're going to change the cos of 50 degrees. The cofunction for cos of 50 degrees, we would just change it like this. You'd say cos of 90 degrees minus what angle gives you 50 degrees? That would be 90 degrees minus 40 degrees. So here's the thing about that. The reason I knew I had to use this one is because we have an angle that is less than 90 degrees. So you have to use the 90 minus theta. If you had an angle that was greater than 90 degrees, okay, but that didn't pass, of course, 180, then you'd use the 90 plus theta. So that's how I knew I had to say 90 minus something, okay. So now that we have this, if you change this to its cofunction, that would be positive sine of 40 degrees, okay, to stay positive. So that is equal to sine 40 degrees, and that is squared. Now we know what sine 40 degrees is. We saw that in the beginning. That is p. So that means that this is actually just p all squared, which is of course just equal to p squared. And that's our answer for that one. Okay, moving on to the next one. Okay, so now we're on 5.1.3 and we have cos of negative 80 degrees. So the angle is negative. When your angle is negative, what should you do? You can add 360 degrees to that. So I'm not even going to just add it and change the number. Look at what we can just do. This is cos 360 degrees minus 80 degrees. Just like you would reduce cos 360 minus theta, this will be reduced to positive cos theta. Since this is in cos quadrant, is the same way this would also be reduced to positive cos 80 degrees. Okay, so remember how I said that all the angles that you have, you should always relate it to 40 degrees because our reference angle is 40 degrees. So how do we relate 80 degrees to 40 degrees? Well, 80 degrees is double of 40. So it means that they're using double angles here. So we can change this to cos of 2 times 40 degrees. And then just change it to one of the double angle formulas that would help you find your answer. I would rather change it to one that has a sine of 40 degrees or sine theta. So I would change it into this one. Remember, cos of 2a can be equal to 1 minus 2 sine squared of a. Okay, and I'll change it to that because I already know what sine a is. So that means this is equal to 1 minus 2 sine squared of 40 degrees. And so this is equal to 1 minus 2. Now I know what sine of 40 degrees is. It's p. And that needs to be squared. So that is just 1 minus 2p squared. And that's your answer in that question. Okay, so that is it for our trig diagram. Then we move on to 5.2. Okay, so now we're on 5.2 and it says given tan x times 1 minus cos squared x plus cos squared x is equal to, and it's equal to this. We have to prove the above identity. Okay, so with trigonometric identities, you have two hand sides that you're really looking at, right? You have to either work with the left or the right hand side. So when you look at this identity, which hand side do you think you can actually simplify further? That would be the left hand side. Because you see, we have things like tan, you have squared, cos squared, and cos squared. These are things that can actually be expanded to something else. So we're going to work with those ones. Okay. With that being said, I'm going to go ahead and start off by just saying my left-hand side is equal to, just so that at the end, I don't really need to say right-hand side equals left-hand side. Okay, so I'm just going to rewrite the left-hand side first. Okay, so now that we have this, you see, we're trying to get the left-hand side to look like the right-hand side. The first thing I see is that the right-hand side has a denominator of cos x. So that's probably... They probably got that because of this tan x. So let's go ahead and expand the tan x. So that is going to be, tan x is sine x over cos x. But the thing is that this is one term on its own. You see that in this expression, you have 1 and 2 terms. So I can just write this as sine x times 1 minus cos squared x. I won't change that yet because I'm not really sure what to do with it yet. And then say over cos x. Okay, so now that we have that, we're going to go to that and say plus, and we have cos squared x. Okay. Now at this point, we have cos x and we want to keep that denominator. So why don't we just try to make the denominators the same and make this one also have a denominator of cos x. But there's one thing I see here. I don't really want this to become cos cubed x, okay? Because there's nothing like that here on our right hand side. So what we can do is, I also noticed something here. You see this looks like a result of grouping, right? You must have grouped things together. And the only way you could have gotten this by grouping is if you had 4 terms. So I see that here we don't have 4 terms. Even if I distribute that, right? Even if that denominator wasn't there, if I had to start from here and distribute, we would have had 3 terms, right? Because you see tan x times 1 is just tan x, and then tan x times that would be, negative tan x cos squared x, and then you have that. So you'd have had 3 terms. So I noticed that we would have had 3 terms here, but here clearly we had 4 terms. So we need to change something so that we can have 4 terms. So instead of leaving this as cos x, we can go ahead and change it to its identity. The identity for cos x is 1 minus sine squared x. And I don't have to think about putting a comma because we have a plus here. So the plus is not really going to change anything. Okay, so we can do that. And then let's just put that over 1. And now we can focus on trying to make the denominators the same. Okay, so this is already a cos x. We need to make that denominator the same. So you can multiply the numerator and the denominator by cos x. So we're going to have this. This is sine x times 1 minus cos squared x, and then over cos x. And then here, you see that we have 2 terms and we have 1 term. When you have 2 terms and 1 term, you can actually rewrite it like this. So I'll put the cos x first. And I'm saying it's been multiplied by 1 minus sine squared x, and then all over cos x. Okay, now that the denominators are the same, we can finally now put them together. So that is equal to, and we're going to say, so we have sine x, and then 1 minus cos squared x, and plus cos x, 1 minus sine squared x. And this goes all over cos x. Okay, so here's the thing. Right now, you see those 2 brackets? They're not the same. So we can't even use any taking out a common factor here. So since they're not even working out like this in the way that they are, there's no use of leaving them like that. We need it to look like this. Okay, and you see that you have 4 terms here. So why don't we just, right now we have 2 terms on the numerator. Why don't we just expand this? And then we'll group it differently since it's already not working out in this order that it is in. Okay, grade 12, sometimes this is a trial and error. You just have to try again and just make sure never to try the same thing over and over. If you keep using the same method over and over again and it's not working, then, it's still not going to work. Okay, so sine x times 1, that's sine x. And then sine x times negative cos squared x is negative sine x cos squared x. Then here we get positive cos x. And then when that multiplies, you get negative cos x sine squared x. Okay, so we have 4 terms now. That's a good thing. Like they have 4 terms as well. We knew that when we had them like this, they didn't work out. They didn't really look like that. So I'm going to group them differently now. All I have to do is just change the way it was grouped. At first, these 2 were grouped together clearly. That's why they look like that. So instead, I'm just going to change that. How about we just group this with the last one? Because I see that they do have like terms or really common factors. They have common factors. So I'm going to group those 2 together. Let's go ahead and say sine x, and then put that minus cos x sine squared x. And then here, I don't want to put this 1 in front because it has a negative. And I see that that doesn't really happen here. You see, they both start with a positive number, okay, or positive value. So I'm going to start with this one. Okay, so we say plus cos x, and then we have the minus sine x, and then cos squared x, all over cos x. Okay, so you see, it's really just constantly looking at the expression you have and comparing it to this, okay, and trying to see what we should do next. If you just work through it by just simplifying, most of the time it doesn't always work out. Okay, so here's the groups that we're now creating. We're going to group these 2 together and these 2 together. Okay, so you're going to take out a common factor in each. The common factor in these 2 terms would be sine x. So sine x is common, and then open a bracket. What is left? Well, sine x divided by sine x is 1. And this divided by sine x, you see you have a squared there. One of it would cancel. You just be left with negative cos x and then the remaining sine x. Okay, so that's done. Then here, what is common? Well, we have a cos. So let's take out positive cos x. And then what's left, we're going to have 1. And then what's left there, we'll have negative sine x and cos x. Okay, and that goes all over cos x. Okay, this actually looks good because do you notice that these are the exact same thing? Okay, so we can actually say these brackets are exactly the same. So we're really taking these brackets out as a common factor. So the bracket comes out as a common factor. And so we're going to have the 1 minus, let me just stick to one name of it. Well, here, do you see that it's called sine x cos x? So let's just stick with that. So 1 minus sine x cos x, because cos x, sine x, the same thing. And then open bracket, we have what's left in this term. Okay, since we're taking out the bracket as a common factor in these two terms, we now have two terms in the numerator. So what's left in the first term? You just have the sine x when you take out the bracket as a common factor. And what's left in the second term when you take out the bracket as a common factor? You're left with the cos x. So it's positive cos x left. Okay, so that looks good. All over cos x. Now, if you look at the identity, you see it's exactly the same thing. It's just obviously those ones are switched around. So sine x plus cos x, 1 minus sine x cos x over cos x. And that's what we have as well. It's just switched around. So it's finally equal to the right-hand side. And we've proven the identity. Okay, so that's 5.2.1. And we move on to 5.2.2. So we're on 5.2.2 and it says, for which values of x in the interval where x is an element of negative 180 all the way to 180 degrees will the identity be undefined? Well, to make an identity undefined or an expression to be undefined, if the denominator is equal to 0, so regardless of whatever the numerator is, as long as the denominator is equal to 0, the expression will be undefined. So let's go ahead and look at what the denominator of our expression was all through. You see that the only denominator we had was cos x. So if that is equal to 0, then our expression will be undefined. So that's the equation that we have to find the solution to, okay, for that interval, of course. So we're looking at cos of x being equal to 0, okay. So I posted a video on 2 ways to find the general solution of a trigonometric equation. You can go ahead and check that video out. Okay, the link is in the description, so that you can follow along with the quick method that I'm going to use here. So I'm going to go ahead and just find the reference angle, and we find that by taking cos over. So that's shift cos of the value we have there. Now, if you say shift cos of 0, you're going to get 90 degrees. Okay, so with the way I showed you the quick method, to solve for x, all you're going to say is x is equal to positive or negative 90 degrees. And then plus k of 360 degrees, where k is an element of integers. And now we're just going to find the values of x within this interval. So we can separate it, of course. You can say x is finally equal to, you have either positive 90 degrees plus k 360 degrees, or x is equal to negative 90 degrees plus k of 360 degrees. And we don't have to say that again. We already said it once. Now, if you want to make your angle positive, that's fine. You can go ahead and make it positive. When an angle is negative, you add 360 degrees to make it positive. So x is equal to 360 minus 90 gives you 270 degrees plus k 360 degrees. So this is the general solution so long. We need to find specific solutions for this interval. So how we're going to find that is you can use a number line. I just feel like it's neater to use a number line. So I'm going to start with the first one, where x is equal to 90 degrees plus, and in place of k, we'll put our integer value. Then we have 360 degrees. So using a number line just to have a bit of structure here, you can try substituting 0. If you substitute 0 into here, you see that you're going to get 90 degrees. Okay, now check. Look at your range, the range of answers you're supposed to accept. Numbers that are greater than negative 180 but less than 180, right? So it means that that does work out. We get 90 degrees when we substitute 0. That is a solution. It is within our domain of the restriction that they asked us to stick with. Okay, let's go ahead and try another integer value. You can choose to go to the right or the left. Let's just go to the left. So let's try negative 1. You can only substitute integer values. When you substitute negative 1, let's see what we get. We get negative 270 degrees. Okay, so negative 270 degrees, is that within range? No, okay, it's a bit too far. So negative 180, it has to be greater than negative 180, but less than 180. So this is not going to work. As you can see, you can just put an X here. We will not go further here since this doesn't work. And let's try 1, which is clearly not going to work. If you try 1, you see, you're just going to have where 360 gets added to 90, which is 450. It's too big. It's way out of range. So we're not even going to try 1. So the only solution we get for this one is 90 degrees. Okay, hold on to that. Then we're going to try this one. Okay, again, I'm using a number line. If we substitute 0, you know that that's going to multiply. You're just going to have 270. 270 is too high. It's way out of range. So that's not going to work. Our 270 degrees does not work. Okay, we can try negative numbers. Let's try negative 1, because you see, if you go positive, you're just going to make your angle way too big, and it's just not going to be within the answers that you're looking for. So let's try negative 1. If you substitute negative 1, you get negative 90 degrees, which is good. So we get negative 90 degrees, which works out. Okay, so that is within range. It is greater than negative 180, but less than 180. Okay, so that works. And then since negative 1 worked, you can try negative 2 just to see if it works. Probably not going to, but you see, it's way too far. So negative 2 doesn't work. We don't have to try anything else. So the only solutions for x within that interval is where x is equal to positive 90 degrees or where x is equal to negative 90 degrees. And that's just your answer. Okay, so that would just be another way to find it. Okay, so that is it for that question. And we move on to 5.3. Okay, so we have 5.3, and 5.3 says, given the expression sine 150 plus cos squared x minus 1 over 2. We have 5.3.1 says, without using a calculator, simplify the expression given above to a single trigonometric term in terms of cos 2x. So that seems like the only challenge they're now putting in this expression, where you have to simplify it in terms of cos 2x. So cos 2x has to be in your answer, the simplified answer for this. Okay, let's go ahead and just rewrite this here. Okay, so first thing we can do here is, well, we have sine 150. And sine 150 simplifies to, you can go ahead and simplify it using your reduction. It will simplify to sine of 30 degrees. Then we have plus cos squared x minus 1 all over 2. Okay, what else can we simplify further? Well, the thing is, you have to try and include cos 2x. So the only thing with the variable right now is this. But I see this 1 as a distraction. So you see that we have cos squared x minus 1. Which identity does that remind you of? Do you remember that the identity for sine squared x is equal to 1 minus cos squared x? And of course, we get this from this identity, right? When you say this is equal to 1. So if you make sine squared x the subject and you take cos squared x over, that's how we get that. Okay, so the thing about this right now is that this is cos squared x minus 1, not 1 minus cos squared x. So it's just switched around. So what we can do is put it in this format, right? By putting the 1 first, but the 1 is negative. So we still have sine 30, which simplifies to a half because it's a special angle. Then instead of putting the cos squared, I'll put the minus 1 first, then say plus cos squared x. Now they're in the same order. The 1 is first and then the cos is second. So over 2. Then what we can do to get it to look like that is notice that here your 1 is negative, here it's positive. Here your cos squared x is positive, here it's negative. So it means there's just a common factor of -1 here, and you just have to take that out. So I'm going to take that negative out as a common factor in these two terms. And what we're left with is, now that the negative is out, you have a +1. And here you're going to have a negative cos squared x. Okay, and that goes all over to, now that we have that, 1 minus cos squared x is equal to sine squared x. Okay, so I'm just trying to simplify it in a way that I don't have any numbers that may be a distraction. So that is sine squared x. Okay, so that looks more simple. But now we need to remember that we need to simplify this in a way that it is in terms of cos 2x. Well, for us to include cos 2x, you're going to have to think about what cos 2x is equal to. See, cos 2x is equal to various things. It's a double angle, and so you have your double angle formulas in your formula sheet. So it's equal to these three things. So this is the identities for cos 2x, right? That's what cos 2x is equal to. But you see that here, the variable that we have is sine squared x. So you're going to have to choose one that has sine squared x. So that means you can either choose this one or this one. And honestly, this one looks easier to use because it's just cos squared x minus sine squared x. Okay, so at this point, I'm starting to see that this is not working out. And the reason why is because I didn't consider that we have a half here. See, if we have a half here, we have to find a way to actually simplify that half. And the best way to simplify it is by taking something that has 2 in it. So it has sine squared, but it should have 2 because at some point you're going to divide both sides by 2. So you will have a half. So let's rethink that. Instead of using what we used there, I'm going to just use that. Okay, 1 minus 2 sine squared x. Okay, so this is what we're going for now. So with this, I'm going to try and make sine squared x the subject. So we can take -2 sine squared x over, and that would become +2 sine squared x. And then you see we still have a 1 here, and we can take the cos 2x over. So it's minus cos 2x. Okay, trying to make sine squared x the subject. So you need to get rid of the 2. So divide both sides by 2, and we need that 2. That 2 is going to be very helpful. So sine squared x is equal to 1 minus cos 2x over 2. Okay, so that's going to be very helpful. So now what we have is a half minus, and we're going to subtract by that. So we're subtracting by, on this, we're going to have 1 minus cos 2x over 2. And then remember, everything is being divided by 2. So let me actually put that divided by 2 in blue. So we have over 2. Okay, so let's work with that numerator quickly. So, okay, so because we are dividing by 2, what I'm going to just write this at is a half minus, and we're subtracting by, I'll let this minus affect the numerator. So what I'm going to do here is 1 minus cos 2x and then over 2, right? And I'm going to say we're just dividing by 2. Since we have fractions here, let's just call it 2 over 1 so we can tip and times in the next line. So we'll have a half, and when you distribute this negative, it becomes, well, let's just put it together since the denominators are the same and we're subtracting, right? Let's just put it together. So the common denominator is now 2, and we have on the numerator 1, then a minus, then you see what happens. You have 1 minus cos 2x, which if you distribute, you're going to get minus 1 and then plus cos 2x. And there you see we actually got rid of that 1. Okay, and of course we're still dividing by the 2, but now you can change that. Since you're dividing by a fraction, you tip and times. So you tip the fraction, swap the numerator and denominator, and times, change the division to a multiplication. Okay, so now we have, this is equal to, well, we're going to have here cos 2x, and so it's cos 2x over 2, and we're multiplying by 1 over 2. So numerator times numerator, denominator times denominator. So that's going to give you cos 2x over 4. That's what that actually simplifies to. So that expression in terms of cos 2x is just cos 2x over 4. Okay, moving on to the next question, 5.3.2. Okay, question 5.3.2 says, hence determine the general solution for the same thing we had here, right? And that is now being equated, or it's equal to 1 over 25. Okay, since we already solved for this, we now know it's cos 2x over 4. We're just going to say that this therefore means that we're actually working with this equation, cos 2x over 4 being equal to 1 over 25. Okay, so I have to solve for x here, or find the general solution. So not specific solutions, we're not really just doing that, we're just general solution. So with this, I will go ahead and cross multiply since we have fractions and an equal to sign. So that's going to be 25 cos 2x is equal to 4 times 1 is just 4. We're going to go ahead and just divide both sides by 25. Okay, so that's cos 2x is equal to 4 over 25. Okay, so at this point now you can go ahead and use the method that you want to use based on that video that I made on general solutions, the 2 methods you can use. I'm going to use the quick method. So first going to find the reference angle. The reference angle we find by taking cos over, so that's shift cos of 4 over 25. And this is what we get. Now, the thing about this is because you have 2x here, eventually when you're solving for x, you're going to have to divide by 2. So don't round off yet. So I'm going to leave it as 80.7931 and just show them that I haven't rounded off yet. Then to solve for this, I know that my solution for the reference angle, which is 2x, I'll just say that 2x is equal to, and actually let me just put it here in the middle first. So I'm saying 2x is finally going to be equal to positive or negative of whatever my reference angle is, which is 80.7931. And it keeps going. Then I have to tell them plus k of the amount of degrees that it takes for a cos function to repeat itself, which is 360 degrees. Then I can go ahead and say where k is an element of integers. And now we can go into solving for the general solution. So I like using this method because it's much quicker and it still gets you to the exact same answer. Again, you can watch this video to find out how to work through that, okay? I compare the standard method to this method and show you why this one just is much more simple to use. So we're going to have 2x is either equal to positive of that angle, so 80.7931, keeps going, plus k of 360 degrees, or 2x is equal to the negative of that, so negative 80 degrees, 0.7931, and that keeps going, plus k of 360 degrees. Then remember this angle is negative, so to make it positive, you can go ahead and add 360 degrees. And once you do this, you'll see that it looks exactly like the solutions you would have gotten if you dealt with it using the method where you have to use the reduction, okay? So I'm going to add 360 degrees to that angle, and no problem, I can still get it back if I need it. So when you're adding 360 degrees to this on the calculator, you see here when you add 360 degrees, it makes this sum to be 360 minus 80 degrees, right? 0.7931. So how you can get that answer is simply just on your calculator, you'd press AC, then just say 360 degrees. So I have to say equal to first. 360 degrees minus your answer. So which gives you that, as you can see. So we're just going to say that 2x, our other solution is 2x is equal to 279.2068, and that keeps going, okay? So you will see that you get the exact same solution if you use the other method. Now we just need to solve for x. Here, to solve x, you need to divide both sides by 2 to get rid of the 2 there. So divide both sides by 2. Don't forget to divide that by 2 as well. So x would be equal to, and now just to get that answer back, you can just go ahead and say shift and cos of 4 over 25, because I just don't want to round off yet. I'm taking that, right? That's this 80 points, that, and I'm going to divide it by 2. So you see that it gives us 40 points, and now I can round off to 2 decimal places because this is the final answer. So 40 points, you see if we round the 6 up, it adds a 1 to the 9, but the 9 will become a 10 and add a 1 to the 3. So you have that 4 degrees. Then we'll have plus. If you say k 360 degrees divided by 2, you're going to get k of 180 degrees. Okay, so that's our first solution. Second solution, you need to get that back. So you can just get it back by saying your 360 degrees minus this 80 point to that. But you know you got that by saying shift cos of 4 over 25. So you can just do that. That is back again. Now that you have that answer, you can say is equal to, and then just say divide by 2, because you need to solve for x by dividing both sides by 2. So divide by 2, divide by 2. And so it means that x is equal to 139 point, and it's just going to be 6 or 60 degrees. We can leave it like that. And then we're going to go ahead and say plus k of 180 degrees because that also divides by 2 as well. Let me leave it as 60. Okay, so 60 here, just add a 0, and here I'll just leave it as 40 as well. So 40. Okay, so those will be our general solutions, of course, where k is an element of integers, but we already have that though. So that is the answer for 5.3.2. That's the last question in question 5. And then we move on to question 6. Okay, so we're on question 6, and question 6 says, in the diagram, the graphs of f of x is equal to cos of x plus a and g of x is equal to sine 2x are drawn for the interval where x is an element of negative 180 to 180. Okay, so the graphs intersect at n here, at n, and p. Okay, p and q. So p and q, those are the points of intersection of the graphs. So you see that they include the x values, right? Just not the y values for that, okay? Because the k value is really the same thing. They have the same y value. And so we have p is also turning point of both graphs. Okay. So let's actually just try to figure out what kind of graphs, which is which, and what's actually going on with the graphs. First of all, you see that this is f, right? Cos of x plus a. Now, even if they didn't label it, you can already see that with this one, it has not been the period, right, has not been tampered with. They didn't change the period, meaning it should behave like a normal cos graph. It's just been shifted in some way, either to the left or to the right. So if you look at the intervals that we have, right, 0, we have 180 degrees. The cos graph, right, if you're going from 0 degrees to 360 degrees, it should look like this. So because of that, you should know that the one that is wider, more spread out, is going to be your cos graph, because that one, the period has not been tampered with. This one, the period has, yes, because it's sine 2x, so it would be more narrow. That kind of graph would be more narrow. So you can see that that's the sine graph and that's the cos graph. Okay, so the first question is, write down the period of f. So the period of the cos graph. Like I said, the period was not tampered with. It's still x. You don't have a 2x or a half x or anything like that. It's just x. It's just been shifted only. So the period is the normal period of a cos graph. A cos graph completes a cycle every 360 degrees. So the period is just 360 degrees. Moving on to the next question. The next question is write down the amplitude of g. Okay. So amplitude of g, we can actually look at the amplitude of g by just looking at the equation. The amplitude is going to be the absolute value of whatever your coefficient of that function is. So in front of sine 2x, there's an invisible 1. I say absolute value because sometimes it can be negative, but you don't have to really consider that. You just have to consider that number there. So the amplitude would be 1. That's what it is. So the amplitude is really just the height from the midline, okay, from the middle to the highest point of the graph. And we can even see that in the sine graph. Yes, that is 1. From the middle till the highest point is 1. So that's our amplitude. Okay, so we're just going to tell them it is 1. Moving on to the next question. Then question 6.3 says, write down the value of A. Okay, so the value of A. So now they want to know how that graph is being shifted. Let's just establish something quickly. You see, if the graph was shifted to the left, I want you to know that by that X, right? Instead of having a minus, you're going to have a plus. So X plus whatever A is, right? Or X plus whatever that number will be. And if it was moving to the right, it should say X minus whatever that number is. So in that case, negative whatever your number is would be A. And in this case, positive whatever that number is would be your A. Okay, so let's look at that. How was that graph shifted? What we can do is look at the points that they gave us. We know that this is a cos graph, and you need to remember what a normal cos graph looks like. A normal cos graph, like I already drew before, it looks like this. So till 360 degrees, right? Meaning at 0 degrees, originally the y value is supposed to be 1. So now why don't we just find out where the y value is 1 in our cos graph now? Do you see that your y value is 1 at 45 degrees? This is what this means. So let me highlight that graph. If that y value is 1, and the original one is supposed to actually look like this, where the y value is 1 like that, it means that if this was the original, but now it looks like that, you moved it in which direction? You moved it to the right. By how much degrees? By 45 degrees. Because now you have 45 degrees and 1. It's supposed to be 0 degrees and 1. Okay, so that's actually what that is. So it's moving to the right by 45 degrees. It was moved, shifted to the right by 45 degrees. So it means that here, what we should have, if it moves to the right, you have a minus, right? So it's x minus the 45 degrees. I can erase those now. And so that would mean that the value of A is negative 45 degrees. Okay, so that is the value of A. A is equal to negative 45 degrees. Okay, moving on to the next question. 6.4 says, calculate the value of K, the Y coordinates of N and Q without the use of a calculator. Okay, so it's for 2 marks. If you use a calculator, they'll probably only give you 1 mark for your answer. So without the use of a calculator, let's look at that. So you see K appears here and here. It's always easier to work with it where it is positive, okay, or where the angle is positive, because it'll just be easier to work with. And it's really especially because from here, right, this is within the range of 0 to 180 degrees, or let me rather say 0 to 360 degrees. It's within that range. So it's easier to find angles like that rather than angles that are going like, behind those ones. So with this one, you're going to have to just consider what the graph looked like. You can either look at the sine graph or the cos graph. Honestly, in this case, I feel like because this is such a weird angle, they gave 165 degrees. Because I know this one moved, the cos graph moved 45 degrees to the right, I think I would rather use the cos graph because it has a 165 degrees, which has a 45 degrees in there. So it's easier to work with. So let's look at this, right? And just to figure out what K is, you have to think about, because we're not using a calculator, you have to think about what the original graph looked like. Again, the original graph actually looked like this. It was shifted 45 degrees to the right. So let's think about what the Y value for 165 degrees would have been. But think about it like this. This graph originally looked like this. It's going to go 45 degrees like that. So if you have 165 degrees and K, you see this value of K, the original function would have had this same value at 45 degrees before this. Okay, since your graph was shifted 45 degrees to the right, if you want to find out where that value of K is, you're going to have to take 165 and go 45 degrees before this, and then you find that. So if we go 45 degrees behind, we end up here and we'll find out what that is. Okay, so 165 minus 45, because we're going 45 degrees backwards, that would be 120. So you have to now think about what the original function would have had at 120 degrees. In other words, what is cos 120 degrees? But remember, they said don't use a calculator. So let's work that out. So now we know to find that, we just need to find cos 120 degrees. Let's go ahead and reduce, because that's all we have to do now to actually find that without using a calculator. So to reduce that, you see that 120 degrees would lie in sine quadrant because it's greater than 90 but less than 180. So you have to use this reduction for it. So that is cos of 180 degrees minus what gives you 120? That's cos 180 minus 60 degrees. And so if you reduce that, because it's not in cos's quadrant but in sine's quadrant, it's going to get reduced to negative cos of 60 degrees. Okay, so now that we have negative cos of 60 degrees, use special angles to find cos 60. So it's going to be negative, this is the value of k, of course, right? K is equal to this. Okay, so with cos 60, you can use a calculator, but I'm also going to just show you the method that I use to calculate this. I don't use the circle. I use something called the OHA rule. So the OHA rule, the O is for opposite, hypotenuse, adjacent, okay? Then we're going to put 30 degrees, 60 degrees, and 45 degrees. I'm just including this so that you can have a way to find special angles. So I'll tell you the ones that you need to watch out for and the ones that you can actually just use the calculator and it'll still give you the same solution here. So OHA rule, you say OHA 30, 60, 45. Then you say 1, 2, 3, square root the biggest number. Then 3, 2, 1, square root the biggest number in this row. And then 1, 2, 1, square root the biggest number. Okay, so if you're looking for cos of 60 degrees, you know that cos speaks about adjacent over hypotenuse. So we'll go to the 60 degrees and we're going to take the adjacent, which is 1, over the hypotenuse, which is 2. So you see cos of 60 degrees is equal to 1 over 2. Okay, so that's just how to use the OHA rule if you didn't want to use the triangles or the circle. So the ones you should watch out for, you should watch out for this one. The one with 45 degrees, okay? Cos of 45 degrees and sine of 45 degrees. Because those ones, they become 1 over square root of 2, okay? Which if you use the calculator, they would have known you used it because the calculator will rationalize the denominator and make your answer root 2 over 2. So they would know that you used the calculator, okay? So I have seen one case where if you use the calculator, you would have thought you were wrong in your solution. It was a 2 and 3D trigonometry question. I forgot what year that was though. So that's the value of k. K is equal to negative a half. You could have used the calculator for this one. It's not a problem. It wouldn't really affect it. But the OHA rule is good to know as a backup, okay? Okay, that is 6.4. K is equal to negative a half. Moving on to the next question. Okay, so 6.5 we have calculate the value of x if g of x plus 60 degrees is equal to f of x plus 60 degrees and x is an element of negative 45 to 0. So this is one of those questions that is not as complicated as it seems. It's just because they decided to add these. You see, the thing is, they are moving, true, they're moving, it's plus 60, right, by the x, meaning it's moving to the left. Okay, if you have plus 60 or plus by the x, it's moving to the left. If it's minus, it's moving to the right. So the thing about it is they're both moving by the exact same thing. Okay, so all we have to do is, since they're moving by the exact same thing and they're equal, why don't we just find out where g of x is already first of all equal to f of x? Then we can consider the shift. So let's look for where that happens. So where is, now I have to erase that. Where is g of x equal to f of x? Well, it happens at 3 places. It happens here, here, and here, right? So those are the places that they are equal. But now we have to consider the shift. So they said plus 60 degrees, meaning it's moving to what direction? It's 60 degrees to the left because it has plus. So it's taking both graphs and shifting them to the left. So to make this easy, I'm going to highlight both graphs and then we'll move them to the left by 60 degrees. Okay, so here are our graphs. We know all the places they intersect. We're going to move them to the left by 60 degrees. Okay, so let's take a spot that we can actually just focus on and actually nicely move it by 60 degrees. Focus on P, because if you are by P and you're moving 60 degrees to the left, you just have to say the angle at P is 45 degrees. Just go 60 degrees to the left of 45 degrees. So that's 45 degrees minus 60 degrees. So if I pick that, those two graphs only, okay, it's just going to try and select both. So I'm just going to have to show you what's going on. If they both move, right, for each place 60 degrees to the left, this at 45 degrees will not happen here anymore. It will happen 60 degrees to the left, which will land at negative 15 degrees. Okay, 45 minus 60 is negative 15. So it means that they will intersect again at negative 15. Let's keep that in mind. That's where they're going. That's where P is going to be. And the place they intersected before was here at negative 75. They're going to move 60 degrees to the left. So they're going to intersect at, you say, negative 75 minus 60 degrees, which gives us negative 135. So here, that's where they will intersect. That's a new place they would intersect. I just have to do it like this because I can't really move the graphs right now. I thought I was going to be able to, but I can't. So they would move and both of them would intersect here at negative 135 degrees. And then the other point of intersection that we had was this one at 165 degrees. If this moves 60 degrees to the left, you're going to intersect again at 105 degrees. So 165 minus 60, right? 105 is somewhere like here. So they will just both move and like intersect somewhere here again. Now, the question is this. You still have to answer them for this interval. We know the places they're still going to intersect after they shift, but we need to solve for x specifically between negative 45 to 0 degrees. So which of these angles where they intersect is within negative 45 to 0 degrees? That would only be the negative 15. So when they shift and then they, of course, intersect at negative 15 degrees, that's the only one that is within that domain. That's the only one there. So that's our answer, where x is equal to negative 15. We can't take that because negative 35 is way beyond that, and that is still way above that, even if it's 105. Okay, so that's our answer. X is equal to negative 15 degrees. It's really just about moving it. So you need to take a pencil, make sure you're drawing the shifts, and you can see those and you'll be able to answer it. So x is equal to negative 15 degrees. Okay, moving on to the next question. Okay, 6.6. So 6.6 says, without using a calculator, determine the number of solutions the equation square root of sine 2x is equal to sine x plus cos x has in the interval where x is an element of negative 90 to 90 degrees. Clearly show all workings. It's interesting how they don't tell you to solve just for x. They're saying determine the number of solutions. Okay, let's just keep that in mind so that we don't forget when we finish solving, to actually count the amount of solutions and tell them that. Okay, so you can see the equation that they gave is one of those ones that they keep bringing up. The grade 12s learn to see the patterns that keep coming up. That's why it's good to do recent papers like 2022, 2023, 24. Okay, it's good to work on this type of papers so that you can see the kind of things they may decide to bring back. So when we look at this equation, yeah, it looks weird. It does look weird. And one of the reasons it looks weird is because of this part. You look at that and you kind of expect them to put some sort of identity so that you can work with it. But we know there's no identity for sine x plus cos x. It's not one, okay? The one that gives you one is sine squared x plus cos squared x. That's the one that gives you one. So it's clearly not that identity. It's not any identity, really. And this will probably lead people to think, is this a trick question? Is there something that we didn't learn? The thing is, the minute I see square root 2, I know they're trying to form something here. They're trying to form, and I see one term and another term. They're probably trying to form a compound angle. So what I'm going to do here is think about square root 2 and just think about what I can do with this number. What can it become? What kind of trig function can it become? What I mean by that is, for example, if you see a half, you can change a half to two things. You can change it to sine of 30 degrees, and you can also change it to cos of 60 degrees because they're both equal to a half. I see square root 2, and I think this type of question has shown up before. I'm not sure if it's in the November paper, it was in the June paper, but there was something like this as well. But they had like a 2. And so the minute you see 2, you're like, okay, maybe it's a half that we have to form from this. But this time they put a square root of 2. So this is where your special angles are going to come in, right? You need to know your special angles well. And again, I've shown you the OHA rule. I'm going to put down the OHA rule here, and we're going to look at which functions have square roots of 2 and try to figure out what they're trying to do here. So here's the OHA rule again. So remember, you say OHA, then you say 30, 60, 45. And you can say 1, 2, 3, 3, 2, 1, 1, 2, 1. And then square root the biggest numbers, okay, not the angles, number in the row, in each row. So that will be the 3 here, and the 2 here. So you see that we have square root of 2, and it appears by the 45 degrees. Okay, so it means that, well, it's not just square root of 2. We have to think about what we can form from this. You can only use cos, sine, or tan. I would not recommend you use tan. Tan is not going to help you here. It's just going to confuse things right now because you see patterns of sine and cos. So let's try what is cos of 45 degrees. We'll also try sine, of course. Cos of 45 degrees, cos is adjacent over hypotenuse. So by the 45 degrees, we take the adjacent, which is a 1, over hypotenuse, which is square root 2. And if you try it with sine as well, sine 45 degrees is 1 as well, the opposite, over hypotenuse, square root 2. So it's the same thing. Okay. So that's probably what they're trying to do. And that makes sense that it's working for cos and sine. So here is the thing. Because we have sine x here plus cos x, this square root 2, it's probably going to form a compound angle over here. So we need it to come here. So we can get it to this side by dividing both sides by the square root of 2. And then what we will have is sine 2x is equal to, now let's be careful how we work with this. Let's take the sine x and divide by square root 2, leaving you with sine x over root 2. And do the same with the cos, leaving you with cos x over root 2. Now, we can actually form compound angle here using these. Because root 2 is the denominator, you can actually see it like this. You actually have an invisible 1 in front of the sine x and an invisible 1 in front of the cos x, meaning we have sine 2x being equal to 1. How about we let the 1 take the denominator of root 2? So 1 over root 2, then sine x, then plus, also do the same thing there, 1 over root 2 cos x. Okay, we're almost there. The 1 over root 2, we can change them so that we can form compound angle formula here. So because we have a sine here, right, I don't want to change it to sine, sine, cos, cos. How about we leave this sine here and change this one to cos? You know that 1 over root 2 can be changed to cos 45 degrees. So that's what I'm going to do there. Let me just write it in the next line. So here, I'm going to go ahead and say that becomes, well, let me put the sine first so that it's in the right order. So sine x, then the 1 over root 2 is now going to be the cos 45 degrees. And this is perfect because they're the same angle. So it's going to work perfectly for compound angle. So sine cos, then you need to have cos sine. So plus, I'll leave the cos here, cos x. And then the 1 over root 2, I will change that to the sine so that it follows the compound angle for sine. Okay, so that's sine 45 degrees. Okay, so do you see now that that looks like sine A cos B plus cos A sine B. And because it follows that rule, the same way this simplifies to sine of A plus B is the same way that on top is going to now simplify to, so we still have sine 2x here. That is now going to simplify to sine x plus 45 degrees. There we go. And that's how we get it to look like that. So the reason we know immediately that there was something to do with compound angles because of this. There's no identity for this. The minute you see a number like root 2 or root 3, you know that they have used, or even 2, right? You know that they've used special angles. So this is what we have. Okay, so let's not lose track of what we're trying to do. What we're trying to do is determine the number of solutions. So we just need to solve for x, find out how many solutions we have within this interval, of course. Okay, so this is a general solution. You just have to solve for x in this general solution. Let's go ahead. We have sine on both sides. This is one of those ones that is taught in grade 11. So the thing is that a textbook, and let me just recommend a textbook that is very, very helpful. The Kevin Smith textbook, that textbook is extremely helpful. It actually has questions like this in the grade 11 one. So if you're matric, if you have access to that textbook, that's very helpful, the grade 11 and 12 one. So I would honestly encourage you to really self-study, because the thing about matric is that there's a lot of work. Many a times teachers don't actually finish the whole curriculum. Okay, so with this, let's actually just go ahead and solve for x. Let's not change this, because if you change this, okay, you're going to have a cos x, and then that just complicates things more. Let's go ahead and try and start solving for this. So with equations like this, right, I know that you have sine and sine. That's not a problem. We are actually just going to find the reference angle first. So this is what I'm going to do. I'm saying reference angle is equal to, right? Then I'm going to take this sine over, and it's going to become shift sine. But the thing about this is it's the inverse of sine. So what it will do to this is that it's going to cancel out this sine, and you will just be left with your angle. So now do you see why our reference angle is going to be x plus 45 degrees? Okay, so reference angle is equal to x plus 45 degrees. Now when we're solving for x, we're going to do this. When you're solving for x, you see the angle, right? The angle that you took the sine over for, right? 2x. That is what you're going to say here. That's what you're going to put as your x, right? Like when we used to say x is equal to, then we go ahead and start solving. That is your x there. So in this case, I say 2x is equal to, and then I'm going to put down my reference angle. Okay, so remember that I'm using the quick way of working this out. Remember, here is that video again, just to remind you about it. You can go ahead and look at that and work on that, because I want to make this as simple as possible. I don't want to use long methods because I want to avoid making mistakes. So what I'm going to say here is, I know that this is my reference angle, but remember that with the function sine, you're only going to use two things, okay? When you're solving for your angle, whatever it is, theta or x, you say your reference angle, then just plus k 360 degrees, or theta is equal to 180 degrees minus your reference angle, okay, plus k 360 degrees, where k is an element of integers. That's what you're going to do. So that's what we're going to do here. Our reference angle is the x plus 45 degrees. So I'll take it like that. X plus 45 degrees. And then I'm saying plus k of 360 degrees. K 360 degrees. Or, hey, my second solution, remember, this is like your x that you're working with, okay? So it's 2x is equal to, and then we're going to take 180 degrees and subtract by our reference angle. Our reference angle has two terms, so you need to use brackets to protect it. So x plus 45 degrees, then plus k 360 degrees, where k is an element of integers, okay? So that was just how to do that. You can check out that video to work on that. I just use that method instead. Now we're just solving. Okay, so the first one, you see that you can take x over. If you take x over, it becomes a negative x. 2x minus x is just x. Okay, then we have 45 degrees plus K 360 degrees. That's all we have there. Okay, then, or in this case, this one is just going to take longer, but it's fine. We're going to have 2x is equal to 180 degrees. Let's go ahead and distribute. So you have minus x and distribute minus 45 degrees. Then plus k of 360 degrees. Okay, 2x is equal to, so 180 degrees minus 45 degrees gives you 135 degrees. And you still have that minus x, which we can take over. So we still have the 2x here. And we're taking the negative x over and because a positive x. Okay. And then we have plus k of 360 degrees. Okay. Then that becomes a 3x is equal to 135 degrees. That's k of 360 degrees. So you see here, to solve for x, you need to divide both sides of the equation by 3. So this would mean that x is equal to, what's the 135 divided by? It's actually, I think it's 45. 135 divided by 3. Yeah, 45. Okay, so we have 45 degrees. And you must also divide the K 360 by 3, which is K 120 degrees. Okay, so there. These are our two solutions. But we're not done because they said, oh, this is such a long question. They said determine the number of solutions. So we still need to find the solutions we will have within this interval. So I've done this already in this trigonometry section, okay, where we're just substituting integer values for k. Okay, so we're starting off with this one, and we need to only accept answers that are greater than negative 90, but less than 90 degrees. So here we go. So 45 plus, and we're going to substitute k value. So again, I like to use a number line because it's just neater. So let's try 0. So you substitute 0, you see that you get 45 degrees. Does that lie within that interval? Let me actually just push this here so we can always check it. Does that lie within that interval? Yes, 45 degrees does work out for that. So 45 degrees is one of the solutions we have. I'll put a check mark on it so I know that it's our answer. Then let's go negative. Let's try negative 1. So minus 1, you get negative 315. It's way too far. Because negative 1 doesn't work, don't try negative 2. Then you can try positive 1. Okay, so I'm just trying to show you a clean method of working through it if you didn't want to like think the answers through like that. Okay, it's better to just be careful. Then if I try positive 1, it's obviously too big, so we're not even going to try that. So right now for this one, this is the only solution we have. Okay, let's go ahead and work with this one where we have x is equal to 45 degrees again, but this time k of 120 degrees. So I'm just going to change that to 120 degrees. So that's just 1, 2. Okay, so let's go ahead and try 0. Would of course work. So again, you're going to have an answer of 45 degrees. I'm not going to repeat that answer. Well, I can, it's fine. 45 degrees worked. Then let's try negative 1. If you say minus 1, you get negative 75 degrees. Does that fall within your domain that they gave you? Yes, it does. Okay, it is greater than negative 90, but less than 90. So negative 1 works. Negative 75 degrees, that is a solution. Of course, if you try negative 2, it's not going to work. It's too far. You see, negative 195, negative 2 does not work. Then we can try 1. I actually did try 1. It didn't work. It's too far. Okay, it's too big. So it must be less than 90. So you see that we have, our solutions are x is equal to 45 degrees, or you don't have to repeat the 45 degrees again, or x is equal to negative 75 degrees. So our solution is, the question is, how many? Determine the number of solutions. We will have 2 solutions. So I'll just conclude. We will have 2 solutions, or there will be 2 solutions. Okay, so that is the answer to that one. Hopefully there weren't mistakes. If there are mistakes, grade 12s, please do let me know. Okay, so that is it for that question. And that is it for question 6. And we move on to the final part of trigonometry, which is question 7. Okay, so we are finally on question 7, which is the last question for trigonometry. So question 7.1 says, in the diagram, triangle ABC is drawn. We have AD is drawn such that AD is perpendicular to BC. So That is our perpendicular height for our triangle there. Okay, so they want us to use the diagram above to determine AD in terms of sine of angle B. Okay, so determine AD. Now, the good thing about this is if you're determining AB in terms of sine of angle B, you're really just working with this right angle, which is nice. So you're working with the right angle and you're trying to include sine of B, right? You're trying to solve for sine of B, make that the subject, and it should include AD. So what we can do here is, why don't we, because they already told us sine of angle B, they're already solving it for us, honestly. They're making this very simple. They told us, say sine of angle B. So sine angle B is equal to, now you know sine is opposite over hypotenuse. So just use that. This is a right angle triangle. The opposite is AD. So that's AD over the hypotenuse, which is AB. That's what they want us to do. And so the question is really just, use the diagram above to determine AD in terms of sine of angle B. Okay, so now we have to just simplify by making AD the subject, because they say determine AD in terms of sine of angle B, meaning that should be part of your answer, but that's your subject. Okay, we can do that by cross multiplying. So sine of angle B as a fraction is sine of angle B over 1. Then cross multiply. 1 times AD is AD. Here, AD is already your subject. And then multiply across like that. Sine of angle B times AB is AB sine angle B. Done. And that is our answer. Okay, moving on to the next question. The next question, 7.1.2, says, hence prove that the area of triangle ABC is equal to a half times BC times AB times sine of angle B. Prove that it looks like they're using the area rule. If you look at that, because it's a half times BC, which is this side, times AB, that side, and the sine of the center angle. But they say prove though. So it has to do with, if it's only for 1 mark, there's no way they want us to use the area rule. Because if you're using the area rule, then this is it. No, there's nothing to prove. So let me think about this. Oh, okay. So I see they're really just asking us to use what we had used here. If this is a perpendicular height, AD, which is what we just found, right? How would you find the area of a triangle? You find the area of a triangle by saying area of a triangle is naturally going to be equal to a half multiplied by the base multiplied by the height. Okay, I guess this is the proof of the area rule. Okay, the one without the perpendicular height. And then we're specifically looking for the area of triangle ABC. And that is a half multiplied by, what's our base there? Our base of this triangle is BC. So multiply by BC, multiply by our perpendicular height, which was AD, which is AD. But you remember that they told us to solve for AD in terms of sine of angle B. So let's use that. Okay, I will say times AD first. Okay, then I'll substitute. So it's equal to a half. Since they use brackets, we might as well just do that as well. Half bracket BC times AD. But now we know what AD is. AD is AB sine angle B. So that's AB, right? Sine angle B. Yeah, that's really what they're saying. And there. So that's actually really the proof. We just substituted AD, okay, with what it was equal to. And we got exactly what they asked for. Okay, that is for 1 mark. Moving on to the next question. Okay, now we're on 7.2 and it says, in the diagram, points B, C, and D lie in the same horizontal plane. Okay, B, C, and D. I don't like that this is so dark, but okay. Then they tell us that ADB, that angle is equal to ACB, and they're both equal to alpha. Then CDB, so angle CDB is equal to theta and DC is equal to K, okay? It's K units. So dB is equal to BC. dB equal to BC. I'm going to mark that in red because, like, it's quite dark to see. Okay, the first question is for us to prove that AD is equal to AC. To prove AD equals AC. Thing is, we just have a big triangle if you look at it like, because it's a 3D shape, right? There's the face of it, which is the big triangle, ADC, right? This is like a triangular prism sort of shape. There's that big shape in front. Then there's this right angle here and that right angle. So I see that AD is part of the triangle ABD and AC is part of the triangle ABC. Do you see that those triangles, they both have alpha and alpha, 90 and 90, and the same angle? So it means they're congruent. So how we can prove that these two lines are equal is to prove that these two triangles are congruent. So it would mean that these two lines are equal. So I'll just, well, this is not Euclid. I don't know if I need reasons, but okay. In triangle ABD and triangle I want to name it in the same way, ABD. So ABC. Okay, so what we have there is let's start with the fact that we have a side, right, that is being shared. AB is a shared side between these two triangles, that one and that one. Okay, so AB is equal to AB. I'll just put reasons. So it's because it's a shared or common side, shared side. Then we have equal angles as well. So alpha and alpha. So ADB, angle ADB is equal to angle ACB, and they both equal to alpha. Okay, that is a given angle. We didn't find that. That was already there. What else is equal in these two triangles? Well, they both have 90 degrees. So we have 90 degrees there. So let's just go ahead and tell them that. I guess we can call it angle ABD. So ABD is equal to angle ABC. Angle ABC. And that's both equal to 90 degrees. And that is given as well because they showed us the sign of 90 degrees there. So given angle. So that would mean that these two triangles are congruent. So it means triangle ABD is, I feel like I didn't need to do this is 2 marks. I feel like I was just supposed to tell them they're congruent. So I'm wasting a lot of time here. So congruent to triangle ABC. I don't have to do this. There's no proving stuff, but maybe they still give a mark for it. I guess so. Because they did say prove. So because they're congruent, it means all their corresponding sides and angles are equal. So AD must be equal to AC now. They're both equal. Let me give it different markings. Okay, so that therefore means that, okay, I have to give the reason for them here. So they are congruent because of side, angle, angle. Okay, so it's side, I'll just say angle, angle. That's the reason. And so because they're congruent, all their corresponding sides and angles are equal, therefore AD must be equal to AC because of congruent triangles. Okay, there. So proven that those two are equal. Moving on to the next question. The next question is prove that BD is equal to K over 2 cos theta. So theta is included in this story now. So these two are equal already. They want us to find BD. BD is this line here. So find that line. I have to really just find that it's equal to that K over 2 cos theta. Okay, let's look at that. How can we find that? So I don't want to find it using this triangle. And the reason why is because if I use this triangle, it's going to be in terms of alpha. Here's in terms of theta. So clearly they didn't use that. If we try to use this triangle like this, we're only going to, I can only think about using the sine rule. And if we're using the sine rule, we have to get this. Because with the sine rule, you need the angle and the side opposite it, the angle and the side opposite it. I don't know where BC comes into the story. but BC is also the same length as BD. So let me look at this again for a while. Okay, so I see a way to find this. What we can do is, because I noticed that there's a 2 and I was like, where's this 2 coming from? Why do we have theta? So I kept focusing on the dark triangle because it's the only one with theta, right? So because of that, I was wondering, where is this 2 coming from? And I decided the only way I can have, a cos theta safely is if I have a right angle triangle, because then I can just use trig functions on it. For example, if I was looking at alpha and I wanted maybe include AB, I could just say something like sine of alpha is equal to, so I'll take the opposite over the hypotenuse, you see, so it's like AB over AD. See, that's how you can get a single term like that when you have a right angle triangle. So what I decided to do is, let's look at this triangle. This is an isosceles triangle, meaning we can cut it in half. And if we cut it in half, you will only be able to do so with a perpendicular bisector. So we're going to use that. That line will be perpendicular to the base. And we've cut this triangle in half. Now we're going to use it like that. Now I know we don't know what this is called. We don't know what this is. However, if you cut it in half, remember this full length was K. It means that half of it would just be a half K, which you can actually call K over 2. Okay, see, a half K is K over 2 because the half is just 1 over 2. The K is really K over 1. If you multiply, 1 times K is K, 2 times 1 is 2. So that's why it's K over 2. Okay, so I decided, since we have K over 2, you see that there, let's include this length of this, okay, that length, and let's include alpha and use that to find dB. So if you look at the sides we're using, so alpha is here, right? That's your reference angle. And then you're using this side here, which is the side that is adjacent alpha. So that's the adjacent side. And you're using this dB because they want you to solve for BD or dB, right? That is your hypotenuse. So if you're using your adjacent and your hypotenuse, you have to use the function cos, because cos is adjacent over hypotenuse. So we can just say, to find that, let's go ahead and say BD. No, now I have to say cos of theta, right? Because I'm using cos theta is equal to the adjacent over the hypotenuse. Okay, so that is going to be, my adjacent side is K over 2. So cos theta is equal to K over 2, okay, over your hypotenuse. Your hypotenuse is the dB, so over hypotenuse. So with that, I can just say over hypotenuse dB or BD. Keep calling it dB. Okay, now the over is really a divided by, or dividing. So we can simplify this further, and we just have to make BD the subject. When we're simplifying, this is a fraction. You can make this one a fraction by putting it over 1. So it means that cos theta is equal to K over 2. Then the division, and we're going to tip in times since we're dividing by a fraction. So you tip the fraction, is 1 over BD, and then you times. Okay, so that means we have cos theta being equal to K times 1 is K, 2 times BD is BD, 2BD, right? And now you just have to make that the subject. So you can make that the subject by cross multiplying. So put cos theta over 1 to make them both fractions. Then cross multiply. 1 times K is K. I'll leave that K there. And then we have cos theta times 2BD, which is 2BD cos theta. Okay. Then we need to make BD the subject. So clearly we need to divide both sides by 2 cos theta to get rid of that. So 2 cos theta. And so therefore BD is equal to K over 2 cos theta. And there we go. So this one we just had to do some construction, just cutting that triangle in half. Okay, there we go. So that is that question. Then we move on to the last question in question 7. Okay, so now we're on the last question, 7.2.3, and it says determine the area of triangle BCD in terms of K and a single trigonometric ratio of theta. Okay, so they want it in terms of K first of all, and it just needs to have a single trigonometric ratio of theta. Okay, so let's go ahead and look at our triangle. They say triangle BCD, this triangle here. So how we can find the area? Okay, we can just use the area rule. Since this is what we have, they want it as a single trig ratio of theta and in terms of K. In the previous question, they asked us to find dB. So we know what dB is now. So we're going to use that. And then you can use this as your center angle. You can use theta as your center angle and then this as the other. So remember that rule works like this. If you have a triangle and you have the middle angle, you have two sides next to that angle, then you're going to use that area rule, half times the one side times the other side and sine of that center angle. Okay, so that's what we're going to use. So remember the one side that we have is DC, right? Not this little thing because this is just K over 2. We're getting the area of this entire shape. So we use that, the full length of K, and then that center angle, theta. Okay, so let's go ahead. We're just going to say that this is going to be equal to, so the area of triangle BCD should be equal to a half multiplied by the one side, which was DB, remember, or BD, right, which is K over 2 cos theta. So that's the K over 2 cos theta, and then multiplied by the other side. So that was BD that we just did. So BD, and then multiplied by the other side of the triangle, which is this full length, which is K, right? So multiply by K, and then the center angle, of course, which is sine theta. Okay, so that's the middle angle that we have there. So that's the whole calculation really. So now we just have to simplify this. So to simplify this, we've got fractions. So we might as well put this as a fraction by putting it over 1. Then we're just going to multiply all through. So 1 times K sine theta would give you K squared sine theta. Then over, let me just use the space. So over, and then 2 times cos theta times 1 is just going to give you 4 cos theta. Okay, then I see here that sine theta and cos theta here as a fraction, and we know that that can become tan theta. So our answer is really just K squared over 4 tan theta. And that is the area of triangle BCD in terms of K and as a single trig ratio of theta. Okay, so that is it for this paper. And I'm still working on the Euclidean geometry. Well, let me just be honest, I've not been working on it because I've been really busy at work. So this weekend, I think I'll be able to get it done. So I'll just go ahead and record it, edit it, and I'll do my best to post it so that you guys can use it to practice before Monday in case there are any grade 12s that are writing on Monday. It will also help a lot if you guys can comment in the comment section the dates that you are writing. You don't have to write the schools, you just have to write the date that you're going to write so that I can also just kind of have a deadline. Okay, I hope you guys enjoyed this video and I will see you guys in the future videos. Bye for now.